Welcome back. Starting from this episode, we're going to talk about the PCB components of the microcontroller we decided to build. Having left off where we left off, the best module to start with is the program counter. You might remember these logic gate demonstration boards. There was this big one which had some logic gates built with transistors and resistors only, and then there were the others. There was this green one which has a NAND chip on it. Then there was the D-latch built from discrete components, and there were two application examples, both of which have something to do with the program counter. Now we have seen that a binary counter is just a bunch of flip-flops connected together, and 8 of these add up to form a register. Each flip-flop in the register represents a bit of the counter. The output of the flip-flop is connected to the input of the next one in the chain. So when an input pulse is applied to the counter, it causes the counter to increment by 1, and the output of each flip-flop changes according to the binary value of the new count. Before I go into showing and decoding what the LEDs are actually displaying, I want to talk a bit about hexadecimal number representation, which is absolutely great for several reasons. It is compact, it is readable, bit manipulation is straightforward, and the whole thing is human-friendly. Hexadecimal representation is a compact way to express large binary numbers. Each hexadecimal digit corresponds to 4 binary bits. This allows for a more condensed representation compared to binary or decimal. This compactness makes hexadecimal numbers easier to read and write, especially when dealing with long binary sequences such as memory ranges or data ranges. The numbers shown in red are actually the powers of 2. I listed them, and I'm going to pick a random decimal number. I'm going to convert it to hexadecimal in the most peculiar way ever. I'm going to compare my number to the red numbers and do one of the following. I will write a 0 next to the red number where the red number is greater than my number. I will write a 1 next to the red number where my number is greater than the red number. Also, I'm going to subtract the red number from my number after that. The result will be the base of the next comparisons, and the procedure goes on until the result of the subtraction is 0. After all this is done, we will have a 16-bit binary sequence, and we're going to use the cheat sheet to turn it into hexadecimal. This is the exact same circuit as before, but this time a 7-segment display was added to display the numbers in hexadecimal. The counter steps through the cheat sheet table, and the same equivalence can be seen on the binary and the hexadecimal displays. I will draw a block diagram of our program counter. These counters I am drawing are all 74LS193 4-bit presettable binary counters. This is what I decided to use in the end. The pins marked with Q are all outputs, and we have 4 of them, Q1, 2, 3, and 4. We also have clock and carry inputs that we use to advance the counter in the desired direction. That's mostly upwards. The carry pin of one stage will go on to drive the clock input of the next stage, so we will build up the 16-bit counter using 4 chips. The clock signal looks like this, and for the sake of the example we will need at least 16 pulses. I want to show you how the counter output will look exactly like what we drew for ourselves earlier on the hexadecimal cheat sheet. I will try to draw some sort of oscillogram for the output so we can follow what stage the counter is going through. Here goes Q1. Q2. Q3. And Q4. These are the first 4 bits of our program counter. If the clock is coming in forever, then this pattern will repeat forever. I'm going to write the binary values of the signals on the diagram directly so we can identify our cheat sheet we created earlier. It is the exact same sequence of numbers. Now, if you plan to extend this into an 8 or 16-bit version, we will need to route the carry bit of the first stage to the clock input of the next stage. The carry bit produces an impulse when an overflow condition occurs. Connecting this to the second stage's clock will increment the second stage every time the first stage overflows, and an 8-bit number is created. If 4 such chips are cascaded, the counter output will be of 16 bits. We also have A, B, C, D and load inputs. A, B, C and D are marked with red on the drawing. The values of these pins will be copied to the counter output when the correct signal is given on the load pin. I am not going to overcomplicate the drawing with the load inputs biased to certain values. I will use the same number 9546 hexadecimal we had with the cheat sheet. Imagine the red preset pins 1, 2, 3 and 4 of the first stage are set to 0, 1, 1, 0. This will be the least significant nibble of the 16-bit counter. So it's gonna be 6 hexadecimal. The next will be 0, 1, 0, 0, which is 4 in hexadecimal. The next two nibbles will be 5 and 9 respectively. Let's take a look how this program counter integrates into our design so far. We have the program counter with a bunch of control signals. We have counter step, clear and load. We have the preset bus and the counter output bus, both of which are 16 bits in width. The counter output will go to the program memory address input bus, and by incrementing and presetting this bus to certain values, we're going to have different outputs sent to the data bus of the program memory. This data bus will be where the instructions will be sent out, encoded, of course. We will write our program or our instructions into the flash memory chips, then we will sequence them with the program counter. In order to turn these into PCBs, we are going to draw it into a design program, Altium Designer in this case. I created the symbols and put the schematic together based on the block diagram and the Proteus simulation that were proven to be working. The top level schematic shows the control signals, address and preset buses, and 4 chips cascaded. There are also some LEDs for easier counter output monitoring. I actually regret not adding some LEDs on the preset bus as well, but it's a little late for that now. We're stuck with this PCB for now. Now, in order to stimulate my PCBs, I built a small tool. This is actually a serial port to GPIO converter, if you want to name it something. And it has 2 power pins and some GPIOs brought out on the IDC connector. It has 18 GPIOs and you can do as you please with them. You can turn them on, you can turn them off, you can do any combinations. And this makes it a perfect little tool to stimulate my PCB. Now let's turn the program counter on. And these are the first 3 GPIOs, which in this case will be the step, the latch and the clear pins of the program counter. We actually have 3 commands because we have 3 wires a part of the ground wire. We can load. This is a combination I hard-coded on a breadboard. I can change it, but for now let's just stick with this. I can reset and I can step. Now, of course, I want to be able to step after I do a load. This is also possible. As it appears, we can do anything we want with our counter. We can preset it, we can step it, we can step after a preset, and we also have a clear function we can shoot at to initialize it back to 0. For example, after a power on reset. Having said and shown all these, I think we're done with this episode. The next one will be about the program memory unit, which is the next microcontroller module in the chain. Once we have that up and running, we will create some fancy patterns in the flash and watch the light show on the data bus triggered by the program counter. But that's for the next time.